Where do I even get started? Let's start with a few updates. I got my first quiz in calculus back, and I am elated that I got a perfect score. I think I mentioned before, but I did absolutely awfully on my quizzes last semester in my math class, so this is a big step up for me. This is only the first quiz, I know, but if I can keep this trend going, then it will go a long way towards improving my grade. Secondly, I had my first quiz in statics today. It felt like it went pretty well. I felt very confident on it. I think I knew what I was doing. We'll see what my score is when I get the quiz back. My first midterm is coming up. It is going to be on Calculus 3 next Friday. I'm still debating on how I'm going to prepare for that. The professor has given us a lot of supplemental questions, and there might be a study guide. If there isn't, I can just use the supplemental questions. But I am going to need to work hard to study for this midterm because the score that I get on it will be vital towards the grade that I get at the end of the semester. If I can do very well on this midterm, then that gives me a good shot of doing well in the class, because I will know that what I'm doing to study and review the material is working. Homework-wise, there are two things that I absolutely need to get done by tonight. The calculus homework is due on Thursday, but I actually have a quiz in my discussion section tomorrow, and I find that if I can complete the homework by the quiz, I do much, much better on the quiz. Plus, if I can get it done tonight, it'll be a load off of me later in the week. So that's something that I need to get done. In my public policy and ethics class, there is a one-pager that is due by Thursday. But it is vital to my comprehension and participation of a group project that I'm a part of, so I will need to get at least the rough draft done tonight so that I have something to talk about with my group when we meet tomorrow. So, after I finish reviewing the material here, what I'm going to work on is math homework and that public policy one-pager. I'm very excited for this session tonight, particularly because the room that I am in has an eraser. No more having to use my jacket to clean the whiteboard. Parameterization is when you take a vector and you put it into terms of variables. In algebra, a parametric function is a function whose variables depend on other variables. Parameters. In vectors, it's much the same thing. There are a couple different situations where you can parameterize something. So, let's say that we want to parameterize this and give each and every single variable a unique labeling. This is a line that runs through the point P0 that is parallel to the vector v. I had to move rooms again because the room that I was in was reserved and the reservees claimed to claim that room, but this room is very special. It's got 3 erasers. This room is where all the erasers on campus have been going. Half of me wants to just pirate one of these things, but there are security cameras in here, and the eraser police would come and put me away for 40 years. Thank you, mandatory minimums. So back to what I was saying. The cool thing about parameterization is we can define any point on this particular line by just adding a multiple of the vector v, since v is parallel to the line we're looking at. I just realized that I forgot to put a plus sign here. Don't do that. So, let's say that you want to parameterize a line that goes through the point x0, y0, z0, and is parallel to the vector a, b, c. The second point defining that line will be given to you by this equation. Notice how the coordinates of this new point is given by the addition of the corresponding original coordinate and the product of t and the corresponding vector coordinate. So, let's say we want to parameterize a line through these 2 points. We're going to need 2 things, a point on the line and a vector parallel to the line. For the point, we are just going to use the point A, and for the vector, we are going to define a new vector that runs the length from A to B. All good things must come to an end, but I didn't think that that would end that quickly. The room of many erasers had also been reserved, and I needed to move once again. Although there are a couple upsides. One, this room has 2 erasers. Not the original 3, but still a good amount of erasers. 2, I'm getting plenty of exercise tonight. And 3, this building that I'm in seems pretty empty, so I'm cautiously optimistic of not getting kicked out of this room. So the copying is done. Now, let's get back to what we were doing. It's a little far away. There we go. Finally, after all of that walking and relocating and finding another room, this is the parameterized form of a line going through these 2 points. Here's an example that I thought really exemplified how parameterized lines can be useful. Let's say we want to find a point where the line we previously found intersects the xy plane. On the xy plane, we know that z is equal to 0. And because we parameterized our line, we also know that z is equal to -2 minus t. So we plug 0 in for z in our parameterization equation, and then we solve for the corresponding t. We then take that t value that we found and we plug it back into the parameterization equation. And then after we do that, we finally find the x, y, and z points where the line intersects the xy plane. But now parameterization gets a little bit trickier because we're adding more dimensions. You can use parameters to define what a plane looks like. Let's say that we have a plane that's just, floating out here in 3D space. This plane is happy, like all planes should be, like all people should be. But there's a problem. This plane isn't defined. We don't know where this plane is, what it looks like, where it lies. But that's not something we should be concerned about, because using our new friend parameterization, we can define this plane. Now, let's pick 3 points that are on the plane. It's important to note that any 3 points can define a plane as long as they are not in a straight line. Because if you have 3 points in a straight line, there are an infinite amount of planes that can correspond to that line. All you need to do is just rotate the plane around the line and you've got a new plane. But as long as the 3 points aren't in a line, you're golden. Now we draw a vector between the points A and C and call it R0. Then we draw a vector between the points A and B and call it R. Now we take the cross product of R sub 0 and R to get a vector that is normal to the plane, which we have called N. Pardon my messy drawing, it's getting a little late and I'm getting a little tired, but we gotta get through this, so let's go! Alright, I've made a mistake. We're not going to define the normal vector n at A, we're going to define it at C instead. And here's why. Because if we define the normal vector at C instead of A, we can do something pretty special. Now, we all remember how the dot product of 2 orthogonal vectors is equal to 0. Using that information, we can get our vectors set up to define this plane using parameterization. The base equation for a plane is the dot product of n and the quantity of r sub 0 minus r. It's okay to make mistakes, that's what they all say. To continue, let's arbitrarily give our vectors some coordinates. We plug our new vectors into the parametric equation for a plane. There's a helicopter outside. Looks like the feds finally found me. But before I get arrested, let's finish this problem. So now we do a dot product and get a parametric equation that defines the plane that we're looking for. So we can define any plane that we want using this process if we have one of 2 situations. A, we're given 3 points, or B, we're given 1 point and the vector that is normal to the plane. And I'm going to show you all how to solve both of these situations. Say we want to define a plane that goes through the point 2, 4, -1 and has a normal vector of 2, 3, 4. First, we put our normal vector into familiar parametric terms, A, B, and C. Then we define a new vector that has the same coordinates as A, and that's R. Crap, I've been doing this wrong. You may have noticed by now that my R naught and my R have been flipped around. I noticed that too. I just thought it would be fine as long as I was consistent, but it's not fine, and here's why. Because X is a variable. X naught is a constant. So, it really should be R minus R naught. And I'm going to fix that from here on. So, now we recall our standard equation for a plane. We plug our given coordinates in, then we just distribute and move over the constants to get our final equation. Any 3-coordinate point that meets this equation will be on the plane that we're looking for. So now, instead of being given a single point and a normal vector, we're given 3 points, A, B, and C. So recalling that a plane can be defined by 2 vectors originating from a same point on the plane, let's choose a unifying point. Now, for the sake of convenience, I'm going to choose A. Our first vector, u, is going to be defined by the distance between B and A, and our next vector, v, is going to be defined by the distance between C and A. Then, by computing the cross product, we can find the vector normal to our plane. And that is all the information that we need. If we plug the coordinates of n into a, b, and c, and the coordinates of point A into r sub 0, then we get the final equation for this plane. Studying for calculus is done! Woo! There's no time to get tired. No time, still got 2 more classes and homework to do. Yeah! Alright, statics is next. I need to give my brain a break, and the class today was dominated by our first quiz, so we didn't learn very many new things, but there are still a few new things that we did learn. This is the circle of unit vectors. It's like the circle of life, except more traumatizing. This is a mnemonic device that helps you remember the cross products of unit vectors. If you go in the clockwise direction, your cross product is going to be positive. If you go in the counterclockwise direction, your cross product is going to be negative. For example, I cross j will equal k, but k cross j is going to equal negative I. Again, it's just a mnemonic, but still very useful. Next, we got the briefest of introduction into statics involving rigid bodies. Up until this point, we have been imagining forces being applied all at a single point. That's not the case anymore. Instead, we can have multiple forces acting at multiple different points along a singular body. The only thing that we really learned today was the principle of transmissibility. It states that if you have some force vector being applied somewhere on a rigid body, and if you draw a dotted line parallel to that force vector, you can move that force vector anywhere along the dotted line and it will still have the same effect on the rigid body. Now, if I were to take an educated guess, this would probably allow us to condense all the forces acting upon a rigid body down to a single point. You just draw the lines of transmissibility, and wherever they intersect is where the force is being applied. But again, I haven't been taught that yet. I may be wrong. That took a long time. Alright, so it is now 10 o'clock, and I still technically have physics from today to review. However, the material is kind of complicated, and I think it would be remiss of me to attempt to study that when I'm getting this tired. Instead, I think my time would be much better spent doing homework instead. I only have calculus homework and public policy homework to do. So I think that is going to be it for the night. After this, I'm going to do homework and then go to sleep, man, because it's late. So, thank you so much for watching. I'll see you all tomorrow.